Hello friends, welcome to your channel Aarohi Classes, and in today's lecture we will discuss FRIIS Transmission Line Equation. Okay, so you can see here this is a communication system in which we have a transmitting antenna and the receiving antenna, and the distance between transmitting and receiving antenna is R. Okay, now in this PT is the input power to the transmitting antenna. Okay, and ET is the radiation efficiency of transmitting antenna. Okay, so power density at receiving end for isotropic antenna is W0 equal to ET PT divided by 4 pi R square. Okay, for directional transmitting antenna, power density will be equal to PT GT upon 4 pi R square, and GT is equal to efficiency into directivity. So we can write here ET PT DT divided by 4 pi R square, where DT is the directivity of the transmitting antenna and ET is the efficiency of the transmitting antenna. Effective area of receiving antenna AR equal to ER dr lambda square divided by 4 pi. In previous lecture we have calculated the relation between effective area and the directivity of the antenna. Okay, so effective area is equal to the efficiency into directivity into lambda square divided by 4 pi. So total received power will be PR equal to radiation density of the incoming wave into the effective aperture area of the receiving antenna. Then it will become, put the value of WT and AR, ET ER lambda upon 4 pi R whole square DT dr into PT. PR divided by PT equal to ET ER lambda upon 4 pi R whole square DT into dr. Okay, if we include losses at both ends, then PR divided by PT equal to ER ET 1 minus mod of gamma r square 1 minus mod of gamma t square lambda upon 4 pi r whole square dt dr into rho t dot rho r unit vector whole square. So you can see here, after including losses, the formula will become PR divided by PT equal to ER ET, where ER ET is the radiation efficiency. Radiation efficiency. And 1 minus mod of gamma square, gamma r square, and 1 minus mod of gamma t square. These are the reflection losses. Reflection losses due to mismatch. Okay, if there is a mismatch at the receiving side and mismatch at the transmitting side, then these part will come into the formula 1 minus mod of gamma square and 1 minus mod of gamma t square. These are the reflection losses due to the mismatch. And rho t dot rho r, mod of rho t and rho r whole square, these are the polarization losses. Polarization losses. Okay, if there is a mismatch, or you can say in the orientation of the electric field vector of the transmitting antenna and the receiving antenna, okay, then polarization loss will take place, and this factor will come into the formula mod of rho t dot rho r whole square. If there is no loss, if no loss, PR divided by PT equal to lambda upon 4 pi r square dt dr. Okay, now take the log of on both sides. PR dBm equal to PT dBm plus 20 log base 10 u minus 20 log 4 pi minus 20 log base 10 f minus 20 log base 10 r plus 10 log 10 dt plus 10 log 10 dr. Now you can see here lambda is equal to V by F. Okay, so we have put here lambda equal to V by F, where V is the phase velocity. So it will come 20 when we take the log 20 log 10 u minus 20 log 10 f. Okay, 20 is come because there is a whole square. 20 log 10 u minus 20 log 10 4 pi minus 20 log 10 f minus 20 log 10 r plus 20 log 10 dt plus 20 log 10 dr. This is the FRIIS transmission line equation, in which path loss is defined by path loss, that is equal to 20 log base 10 r plus 20 log 10 f plus 22. Okay, that is the path loss. 20 log 10 r plus 20 log tan f plus 22, that is nothing but 20 log 4 pi. The value of 20 log 4 pi is 22. 20. So this is all about the FRIIS transmission line equation. ओके, आज के वीडियो में बस इतना ही। अगर आपको मेरा वीडियो अच्छा लगा तो प्लीज़ इस वीडियो को लाइक कीजिए, मेरे चैनल को सब्सक्राइब कीजिए और इस वीडियो को शेयर कीजिए। धन्यवाद।